Hi, I'm Jamie. I'm one of the co-founders of Photonics. I'll give you a quick introduction to the company and then focus on the product that we released recently, which is a quantum-focused PDK. So we are primarily focused on being able to quickly design fabrication-tolerant PDKs. So this is targeted both at fabs and PIC designers, but the core capability is this ability to learn about a fabrication process and generate a PDK very quickly. So for foundries, this can fit in as a additional PDK offering, but it's also the turnaround time is fast enough that it can form part of the process optimization. And then we also, coming soon, because we're dealing with so many of our own designs, we've had to build infrastructure to cope with that. And we realized this may be a useful tool for foundries in terms of distributing and managing PDKs. For PIC designers, the offering is very similar, whether it's targeted a custom application or they're doing dedicated wafer runs. But also we realize it makes sense to open up our kind of PDK development pipeline to external users. So that includes, for example, doing wafer scale characterization or access to ADKs or packaging templates. So this maybe for this audience is a bit basic, but really the problem we're setting out to try and solve is to help reduce the number of iterations that are needed to get a functioning PIC product. And this is especially true for the applications where you need to design your PDKs from scratch. So most of the foundries have their own PDKs. They're improving all the time, but they're primarily designed around the telecoms bands, because today that's where the largest portion of the market is. And that means if you want to work away from the telecoms bands, you need to do the development from scratch. So our core technology is this pipeline for PDK development. And what I mean by that is we start by characterizing the fabrication process. So we get some information from the foundry, and we also run like a test run to get some information on our dedicated training patterns. And that forms a training data set for a fabrication process model. So that means for a given foundry, we can know for any target design, how is that design likely to come out when it's manufactured? And more importantly, what's the space of ways that design can come out when it's manufactured? So that then sits as a layer within an optimizer that lets us optimize a component design for some target specifications for the range of ways that we expect that to come out when it's manufactured. And because we can do that massively in parallel, it means we can take a sort of preset library of components and optimize them all in one go. So from there, that gives you a library of GDS files that can be usable, but to sort of make it easier, we integrate that with several of the EDA tools, and this list is growing over time. So what that means is from our website, you can download a package that just plugs into any one of these tools, along with documentation, assembly design kits, tutorials, and then all of the PDKs have like detailed version histories. And then lastly, we close the loop with wafer scale measurement. We need statistical data on these components. So we have a very an automated but very focused testing system to get a high volume of data. So the nice thing is it works. So here are two examples. One is comparing a simple MMI design to the foundry design. And in this case, you see a 4 times performance improvement and a 4 times size reduction. But maybe the more important comparison is comparing this design to, or comparing these designs to designs done via kind of conventional inverse design. And so what we see here, this is on the right-hand side, is comparison between inverse design and our design approach, measured data on the same chips, on the same wafers. The devices are right next to each other. And what we see is about a factor of 2 improvement in the loss. We're much closer to our target ratio, a fraction of a percent versus several percent. And then crucially, for the same amount of process variation, we see about a factor of 2 reduction in the performance variation. So putting that all together into the product release for today, this is our Sync PDK. So it's a PDK developed on a 200 nanometer silicon nitride process. We picked 200 nanometers because it means that it facilitates wavelengths right from the blue-green into the telecom C-band. So we kind of co-developed this process with Cornerstone and used the rapid turnaround time to help optimize the process parameters there. So this PDK allows on the same process to address 33 individual wavelengths targeted at the transition lines of a range of quantum systems, and this will be available on Cornerstone's visible wavelength silicon nitride process, which has its first MPW rates later this year. We also did the same thing for the telecoms bands across four different fabrication processes. And then lastly, all of these PDKs are compatible with our packaging templates, which means for any wavelength you choose or any process you choose, the input and output couplings are optimized for the relevant fiber modes and fiber arrays, and can be packaged in a kind of simple, predefined way with Alta and using Senko's fiber arrays. So thank you. That's it. Let's take any questions.